Hey everybody! So for some of you, second class recording in a week. I mean, that's pretty exciting, I know. But for those of you that are watching this because you missed class or whatever, it'll probably be the same thing, but whatever. So, all right, we talked about that in section 5.2. We spent a lot of time applying Newton's laws. We talk about Newton's first law, inertia, Newton's second law, F equals ma, dealing with acceleration, and then Newton's third law, action-reaction, in section 5.1. And we talked about examples and concepts and how they manifest themselves out there in the real world. But in section 5.2, we apply those ideas to real-life situations and see how they affect motion and why we see certain things that we see. So on Tuesday, we started off talking about different types of forces. And two forces that we introduced on Tuesday were weight and normal force, where weight is the force of gravity, and then normal force is a force that comes from a surface that a lot of times opposes weight, opposes the force of gravity, but not always equal. And we did a couple of examples, one with just real quick to review, right? We talked about this kid sitting in the chair, and in the first example, right, the normal force and the weight were exactly equal to one another so that it balances out on the kid and no acceleration occurs. But in the second example with the chair, there were two forces in the downward direction, and together they give us a total downward force in the negative direction, but the normal force then has to balance both of those forces out to keep the chair from falling through the floor. Right? Normal force perpendicular to the surface. In the case of the kid sitting in the chair, the surface is the chair, but in the case of the kid or the chair sitting on the floor, the surface is the floor. In one case, it exactly balances gravity. In the other case, it doesn't. The second example that we did on Tuesday dealt with this firefighter who was sliding down the pole. Never mind the purple in the bottom corner. That was an example I was talking about at the end of class with a different student. But we talked about the idea that there are, again, two forces acting on this firefighter, one up and one down. The downward force, the weight, is greater than the upward force, which we said in this problem isn't exactly a normal force, even though it points upward. It's really more of a frictional force. But in the case of a downward force greater than an upward force, even if that downward force is gravity, if it's bigger than the upward force, we will get acceleration in the downward direction, and we use that in this problem. The next part of section 5.2, or the next part of this portion of section 5.2, we talked about weight, and we said that weight is the force of gravity. But we have to make a clear distinction because weight and mass are two separate things. In this class, I am very careful about which I use in which situation. Weight, like it says here, as we defined yesterday, weight is a gravitational force. And because it is a force, it is measured in newtons. Now, in America, right, we don't measure things, we don't measure forces in newtons, we measure them in pounds, but it's still measuring a force. However, that is a different unit than mass, right? As it says here, mass is a measure of the inertia of an object, and it is measured in kilograms. So, when we talk about mass, mass is an amount of matter. And we talked about that in the first part, inertia. Inertia is how hard it is to get something to accelerate, to change what it is doing. Objects that have a lot of inertia are hard to start accelerating or start moving, but also they are hard to stop moving. And in that vein too, they would also be hard to change direction, because all of those are acceleration. How much inertia something has is directly related to the amount of matter that comprises that object. Mass is a constant value. that does not change regardless of the location of an object. And it says here, right? Your mass would not change because mass deals with matter. However, the force of gravity is influenced by not only the matter in you, but the other object that you are gravitationally attracted to. The vast majority of our human experience occurs on Earth. So the other object that we are gravitationally attracted to most is Earth. But we'll learn in chapter 8 that there is gravitational attraction between any two objects. And that gravitational attraction depends on the mass of both of those objects and the distance between them. So, if we were to change our location in the universe and become closer, not necessarily that it's not as simple as just being closer, but if we go to the surface of the moon, the gravitational force on the moon is less than the gravitational force on the surface of the Earth. As a result, you would weigh less on the moon than you do on the Earth. Like we talked about yesterday, the weight of an object, I should do this. The weight of an object we define as m times g, where g is the acceleration caused by gravity. But here on Earth, that is a constant value, 9.81 meters per second squared. So we plug that in. The acceleration caused by gravity is always constant, but the magnitude of that acceleration depends on the location where we are in the universe. On the moon, we would still calculate weight as m times g, but the g value, the acceleration of gravity, is different on the moon than it is on Earth. And therefore, the weight of the same object would be different on the moon than it is on the Earth. Not because it's a different object, but because weight is a gravitational force and depends on the gravity at that location. Mass, however, does not change. The mass of this object is always 81 kilograms. Mass is a constant value. Weight, it depends on the situation. So, down at the bottom of page 2, you have practice problem number 20. It says you lift a stuffed suitcase with a force of 105 newtons, giving it an acceleration of 0.705 meters per second squared. Two questions. What is the mass of the suitcase and what is its weight? Now, we just talked about these are two different questions, and they should have two different answers because mass and weight are not the same thing. So for part A, what is the mass? That's our first unknown. But for part B, what is the weight? I said that's a second unknown. Those are two different objects. Okay, couple things that we know here. Okay. First, you lift a stuffed suitcase with a force of 105 newtons. That is the force you are applying to the suitcase. So I'm going to call that F of A because it is an applied force. And it's 105 newtons. That's a magnitude. Let's wait for a free body diagram before we give it direction. And then we give it an acceleration of 0.705 meters per second squared. Again, that's the magnitude. Let's wait for the free body diagram before we give it a direction. So, in this case, they have not provided us with a picture, so it's beneficial for us to draw our own free body diagram. Here's my suitcase, handle. There's my hand. Okay? It says that I'm lifting it with a force of 105 newtons. I called that F of A in my problem, so I will label it as F of A, and I know that that's 105 newtons. Now, a free body diagram shows the forces. There is another force acting on this object. The weight of that object is caused by gravity and therefore acts in a downward direction. We don't know what that value is yet, but we do know that it's equal to m times g. But in this problem, we don't know m, so we really can't figure that out. However, if we're lifting it, okay, now I'm going to add a little bit of detail to this problem. A free body diagram shows forces, but it told us that we have an upwards acceleration, lifting the suitcase, causing it to accelerate in the upwards direction, meaning F of A is going to have to be greater than W in this case to cause the upwards acceleration. Once we've labeled this free body diagram, now we can go about calculating these things. Because we're dealing with acceleration, we can use Newton's second law. Sigma F is equal to m times A. Applying it to our problem specifically, F of A plus W equals m times A. Now, you may say, well, wait a second. Why aren't we subtracting? Let's just relax. Remember that sigma is a summation function. It means add. So set up the equation as addition. Yes, we know that W should be going in the downward direction, but when we solve it, that should really make us come out the way we need to. Okay? All right. Let's start taking this equation and making it even more detailed. Okay? We have two unknowns in that equation. Both W and M are unknowns. But we can take advantage of the way that W, weight, is defined to help us reduce the number of unknowns in this problem. We still have F of A plus, we know that the weight of an object is defined as m times g. We don't know what m is, but we do know that g on Earth is 9.81. And we do know that g on Earth points in the downward direction. So we can substitute into this equation negative 9.81 for g. That's a fact, right? We can plug that into the equation. And then mass is still unknown over here, but we do know that the acceleration of the suitcase is 0.705 in the upwards direction, and that makes it positive. That F of A we know to be 105 newtons, also in the upward direction, so we can make that positive. Okay? So now we've substituted in all the values into the equation that we know, making use of the fact that weight is defined as m times g. So even though we don't know the weight and we don't know the mass, we do know g, and that reduces the number of unknowns in our equation from 1 to 2. Simplifying this equation, we end up with this. Wrong color. That's an equation that only has one unknown in it, and we can solve for that unknown. So we would take the negative minus 9.81 m, add it to both sides. So we'd end up with 105 equals, right? To get that 9.8, or get all the m's on the same side. Ooh. Sorry. Wrong number, or wrong letter. Okay? And then, to get m by itself, right, we would divide both sides by 10.52. And we end up with the mass of our suitcase being 9.98 kilograms. So that can go here, right? That's a kilograms number because it doesn't change. That suitcase would have the same mass regardless of our location. But the weight depends upon the mass of the suitcase, right? So to figure out the weight, we would just multiply that mass by 9.81, and we should end up with 97.9 newtons. Remember, that's a force because it's the force of gravity, and that gives us the weight. Distinction between mass and weight. Mass doesn't change. It's the amount of matter that an object has, also tells you about its inertia. The weight of an object does change depending on the force of gravity at whatever location we're at. The last part of this portion of section 5.2 deals with vertical acceleration. When we draw a free body diagram, the first force that we're going to put on it in almost every situation is the force of gravity, the weight of an object. And that force of gravity within a reasonable distance from the surface is going to remain constant. We'll learn in section 8 or chapter 8 that force of gravity does vary slightly depending on how far off the ground we are, but the variance is so small that we can assume it to be just m times g. But that means that if we want to accelerate in the upward direction, like let's say on an elevator, we have to contend with that force of gravity always acting on our object in a downward direction. What we have to do then is modify the normal force in order to either overcome the weight of an object or reduce the normal force, which makes the downward direction weight force greater than the upward direction, so we can cause acceleration in different directions. This changing of the normal force is what we refer to as apparent weight. Your quote-unquote weight, how much you weigh here on Earth, the scale that you step on that gives your quote-unquote weight doesn't really measure your weight. It doesn't measure the force of gravity pulling down on you. It actually measures the force of the floor pushing up on you. When you're standing with no acceleration in your bathroom, the weight and the normal force are exactly the same. But in a situation where vertical acceleration occurs, the normal force needs to change in order to produce a net force either up or down, depending on how you want to accelerate. That then causes your apparent weight, or what it quote-unquote feels like you weigh, to change. Example. Let's take this picture here that we have, and let's isolate this lady in this roller or this elevator and put it here. But let's say that this elevator isn't an elevator. It's actually the power tower at Cedar Point. Let's say we got on the power tower that shoots you upward from the bottom. There is always, disregard these forces here, there is always, let's not do that. Let's do this. There is always a downward force coming from the weight of the person in the elevator, or the weight of the person on the power tower. That does not change. It is always equal to m times g. Before the ride starts, when you are sitting at rest at the bottom of the power tower, there are two forces acting on you. There is gravitational force pulling down on you, and then the normal force coming from the seat that is exactly balancing you out. Therefore, you do not accelerate. Before the ride starts, you're just sitting there. But once the ride begins, you experience a very large acceleration in the upward direction, right? Being on the power tower that shoots you upward. In order for us to have a very large acceleration in the upward direction, we have to have a very large net force in the upward direction. There are two ways that we could get a net force in the upward direction. One would be for us to shrink the green force, or the green arrow on this free body diagram. But that doesn't happen, because that green arrow represents the gravitational force, or the weight that is pulling down from gravity on Earth. We can't change that, regardless of the situation that we're in, as long as we're relatively close to the surface, and even though the power tower may seem high, it's still close to the surface of the Earth. That means the only other option we have is to increase the normal force acting on you. Remember that normal force gives us the sensation of how much we weigh. Like it says here, the way you experience your weight is from the force exerted upward on your feet by the floor. Weight is actually, quote unquote, apparent weight, or how much you think you weigh, is not due to gravity, it's due to normal force. In this situation, when the power tower is blasting you upward, you have a greater normal force than you do gravity to cause an upwards acceleration. That increases your quote-unquote apparent weight. It makes you, quote unquote, feel heavier. That sensation you experience is getting like pushed down into the seat of the power tower. And it makes you feel heavy. Your mass hasn't changed. Your weight hasn't changed, because those two things, at least on Earth, are constant. Mass is constant everywhere. Your weight on Earth is constant no matter where you are. But the increase in the normal force has caused an increase in your apparent weight. Now, the normal force increase has caused a large upwards acceleration, and it shoots you up in the air. But you have to slow down before you reach the top. If you're moving upwards, if you have velocity in the upward direction, in order to slow down, you need to have acceleration in the downward direction. Right? Velocity and acceleration in different directions results in slowing down. As you're traveling upwards, right, your gravitational force doesn't change. But we can change the normal force. Once there's that big, huge increase at the beginning of normal force to create this sensation that you are heavy, now things change. After that large initial upward acceleration, you feel almost like you're floating as you get to the top. That sensation of feeling lighter than you normally are, like you're not quite attached to the seat anymore. This happens also when you're going over like tops of hills on roller coasters, like those little hills at the end of the Magnum or the Blue Streak, if you're very adventurous and ride the Blue Streak, right? But that feeling that you're not quite attached to your seat anymore comes from the fact that your normal force has decreased. If you're traveling upward, but your normal force decreases, and now there's a greater force down than up, you have a net force. You have a net force in the downward direction. If you have net force in the downward direction, you have acceleration in the downward direction. If you're traveling up and you have acceleration in the downward direction, you slow down. It causes a change in your apparent weight, how much you think you weigh. I changed the color of this object, or of this force. I shouldn't have. There we go. All right. At the top of the power tower, now let's say you get to the top, all right? Let's say you take the other power tower, the one that drops you. You go up to the top, right? And for a brief second, you're sitting up at the top and nothing is happening. Normal force from the seat and weight are completely balanced. No acceleration. You sit up at the top not doing anything. But then, guess what happens? Normal force goes away. And now, the only force acting on you is gravity, your weight. This produces a sensation that we call weightlessness, or you feel weightless. Not because gravity is not acting on you anymore, but because there is no normal force. If you're up at the top of the power tower and you only experience gravity in the downward direction, guess what you're going to do? You're going to accelerate. How much? 9.81 meters per second squared in the downward direction, just like anything else we drop. And at that moment, even though gravity is still acting on you, you feel, quote unquote, weightless because there is no normal force. Now, to slow you back down at the bottom, that normal force needs to come back. And it doesn't just need to come back, it has to get bigger. Because on the way down, you have a velocity in this direction. To slow down, you need to have acceleration in this direction. The only way to get acceleration upward is if you have net force upward, and that only happens if the normal force increases. All right. Let's take a look at how this shows up in a problem. So number 78, which shows up at the back of chapter 5. I think it's page 184, but I'm not 100% sure on that. So anyway, it says, as part of a physics experiment, you stand on a bathroom scale in an elevator. Though your normal weight is 610, the scale reads 730. So two parts. Part A is the acceleration of the elevator at this moment, upward, downward, or zero. There's you. There's the middle of you, which we'll use as the reference point of our coordinate system in this problem. It says your normal weight is 610 newtons, meaning when there is no acceleration up or down, your normal force is 610, which also means that's the force of gravity acting on you. But it says in this problem that the scale is reading 730. We said the scale is a measure of your apparent weight, quote unquote. And we said that your apparent weight, it comes from the normal force. Your book also sometimes likes to label it as W sub A. Those are both the same thing. I like normal force because it's just showing you that it's the same kind of force as before, just in a different way. And it says that your normal force in this case is 730 newtons. So, it's asking you about acceleration. We know back from section 5.1 that acceleration is caused by net force. In this case here, there is a greater force upward than there is downward. My arrows don't exactly show that, but my labeling of the arrows does. So if I have an upward force greater than a downward force, my net force is in the upward direction. And if net force is in the upward direction, acceleration is in the upward direction. So go ahead and take a second. If you need to write that down somehow, go ahead and do it. Part B says calculate the magnitude of the elevator's acceleration. So it wants to know A, how much is the elevator accelerating? If there's acceleration, we know that we can use Newton's second law. This free body diagram we can use to set up this equation. Okay? We know f of n, we know w, but over here on the right-hand side, they didn't really tell us anything about the mass of that object. But remember, if we know that w, the weight, is equal to 610, we can find the mass. All we need to do is take 610 and divide it by 9.81. Right? Because w is equal to m times g, so m is equal to w divided by g. Hopefully you did that real quick in your head. So 730 in the upward direction plus 610 in the downward direction equals the mass, which I calculated to be 62.2 kilograms. And now the only thing we don't know in that equation is A. So we solve that quickly. Hopefully correctly. And I get that the acceleration of that object is positive 1.93 meters per second squared. For letter C, it says, what, if anything, can you say about the velocity of the elevator? And the answer to that is you can't say anything about the velocity for sure. You don't know, that's the only thing you can say for sure is that it's changing because there is acceleration. But remember, we talked about, just because we have come up with something as a positive acceleration doesn't necessarily mean something is speeding up. All we know is that it's accelerating in the positive direction. So for C, the only thing you can really say is that the velocity is changing. Okay, that brings us to the end of this portion of section 5.2 about normal force, weight, and then ultimately apparent weight, which comes from the normal force acting on an object with a vertical acceleration. Checking the calendar, there is a homework assignment for tonight on gravity, weight, normal force, and apparent weight. Couple of conceptual questions, couple of calculations towards the end. Answers are posted, so if you have some issues with that after you check the answers, come in and see me. I'll be back in school before school tomorrow, but also after school today on Wednesday as well. So if you have some problems, come see me, and I will see you guys tomorrow morning.